Hold on. All right. So Roger and we've been talking about some different topics. None of them were quite ready today. And so one of the things that we agreed upon was I think this paper is pretty cool. So I've actually talked about it before. I'm going to talk about it again here. Most of the people here don't necessarily overlap with the other places where I've been talking about this. Um, so this is paper reinforcement learning via self-distillation. And um, the short version is a lot of people are using GRPO in order to teach chain of thought, long chain of thought reasoning to LLMs. And so this would be a direct competitor to GRPO. There's tons and tons of research right now going into RL for LLMs. Not all of it is about reasoning, but there's plenty of it. So on one level, you're like, yeah, but like every week there's 10 papers announced that are some variant of RL um, for LLM. So, what makes this one different? So I have three big pluses for this paper and one minus. So we'll get into the details about how it works and everything. But plus number one, no surprise, um, when they tried using their algorithm, which they call SDPO, they found that SDPO works better than GRPO. Okay, it's a research paper, pretty much you expect them to say. All right. The other thing that's interesting is they found that the LLM improves faster, so it's more sample efficient than GRPO. So that's another plus in there to the extent that this really works for you. The third thing, which is perhaps one of the most interesting things, is that in some of the use cases where they tested it, what they reported is that not only did they get higher scores on some of the benchmarks and things like that, but that with their correct answers, the answers themselves were shorter. They were fewer tokens. And so one of the things you see with reasoning is, people are not 100% sure what the heck the LLM is doing when it's reasoning for longer. Um, there's been several papers, right, that demonstrated that the reasoning chain doesn't actually have to be factually correct. So if you have a problem that says, multiply 5 times parentheses 3 plus 4, we would say, oh, 3 plus 4 is 7, 5 times 7 is 35 or whatever. What we find is that even when those chain of thoughts are wrong, it still helps it get the correct answer in the long run. So we don't really understand this, but one thing that is both a blessing and a curse is that sometimes the model will go down a certain track, and in order to be sure that it's not missing something, it'll backtrack. So the famous thing is you say, like, you see the model outputting tokens saying, wait a minute, or let me try this another way, or whatever. And then it'll go back and it'll do things. And oftentimes what we see is that it'll try two ways or three, four, multiple ways. Um, and the model's actually better at reflecting back upon the things that it tried to see which one it thinks is the best. It's actually better at doing that than it is at the actual generation of the right thing. So that's one thing that seems to help. But they raised, and we'll get to it in the paper, that their correct answers had a whole lot fewer of these pausing, backtracking type words like wait, and those kinds of things. So those are the three pluses that better, faster, more sample efficient, and that it actually managed to get to the correct answer using shorter chains of thought. Again, longer chains of thought seem to work better than shorter ones, but all things being equal, if you can get a correct answer, everyone would rather have it be shorter. So yeah, James, did you have a question?
Yeah. So the part when you said that even if the steps were wrong, it helped it. Was it like, the example that you had, like five open parentheses, three plus two or whatever? Is it something like three plus two is six? And so that was it that type of error, or was it like the steps itself were wrong, like five times three is 15 and five times, and then plus two is 12, or you see what I'm
Yeah.
saying? Like, is the
Mhm, mhm.
methodology was wrong, or was it like some
So
some minor?
the example that example is really small and short, and it probably would not get the right answer if it screwed up the in between steps. Um, but yes, so uh, uh, if the model spits out a bunch of tokens and it says um, 3 plus 4 is 7, and I don't know, 5 plus 7 is 12. It still might get the right answer 35 because what the model says in the chain of thought is not what it's actually doing when it comes up with the answer, right? If you ask me as a human to explain my thought process, steps I'm taking, probably the steps that I'm actually doing are, in fact, how I get to my answer. But the chain of
Yeah,
thought
because
is not a direct literal correspondence to what the LLM is.
right. Yeah, so that's very interesting because it could be, it or whatever. It could be thinking the right thing, but goofing up and actually implementing it versus thinking the wrong thing
Yeah,
and
so
implementing it correctly.
I've heard some people say that when you have longer chains of thought, it's sort of giving the LLM more computation. Because if you think about it, right, a 40 layer LLM has X many flops between its input and its output. And so you can't really change the number of flops of computation. But the more tokens you have, then um, you're actually getting more flops. I'm actually not a huge fan of that mental model. Um, Mine is a little bit more uh, it's not a complete answer, but I have more of a statistical way of thinking about it in that, like, the tokens you predict are all conditioned on your context. Okay. And do you remember there was this hack where they had an input prompt that was just some word repeated like 200 times? I think maybe it was like poem or something like that or whatever. And so they just said like poem, 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 poem. And that was so completely out of distribution that the model had absolutely nothing, no idea what it was supposed to say next. And what what the researchers hypothesized is that the tokens that it spat out next were exact quotes of strings that it saw in its training data. So you couldn't force it to say a particular thing that you wanted, but you could get it to just spit out things that it saw in its training data. Um, and so along those lines, if you have a model that you say 5 times parentheses 3 plus 4, if it has a certain likelihood of reading it left to right and saying, I'm going to do 5 times 3 first, and then I'm going to add 4, which would be the incorrect answer. By adding more tokens to your context, you can actually shift that bias, the likelihood of it doing the multiply first, or doing the add first, or doing some other thing, right? So anyway, yeah, so I feel like it's not about literally how the model computes things, but that it is able to sort of shift its distribution. It's able to sort of self-alter its prior just by spewing out more tokens.
Oh,
And so
thanks.
to a certain, yeah, and so to a certain degree, like, even if it just output poem, poem, poem 100 times, that would be shifting its distribution. You might think like, well, it's not saying anything intelligent. It's not helping figure out for a more complex problem, what are the 7 steps that need to happen to solve this? But it is still biasing, changing its distribution. So,
Ted, can I inject
uh,
one other thought on that?
yeah,
Is
please.
when it's doing chain of thought, there is information flow through the prediction of the token, and that being the input of the next one. There's information flow that direction, and that's the information flow that we can see. But it occurs to me that there's also still attention that's internal. You can't attend to lower levels, but you certainly could feed information forward and build it up through the attention mechanism. So it may be, and that's kind of hidden. We don't see that. So yeah, I just kind of wonder maybe that's where the correct answer is coming from, and the other is just a red herring and the visible flow.
Yeah, all super interesting. So again, to recap, um, better answers, um, answers faster, more sample. The training is more sample efficient, and shorter generation. So those are 3 pluses. So what we're going to see, though, the one big minus for this compared to GRPO is that because we are doing a form of distillation, there's this idea of a teacher and a student, and so you're going to use more memory because you have this teacher concept. We'll see exactly how the teacher works. I think that there are ways of vanilla. If you use the paper's code implementation, you're going to double the amount of memory. But I think there's probably ways in which it would be a little bit more efficient by not having to exactly double. All right, so let's talk about the abstract real quick. So current methods for reinforcement learning with verifiable rewards. This is our GRPO that we train it on tasks that we know we can verify whether the answer was correct or not. So math problems, coding problems, you can run the code on a number of test cases and check to see if it gets the right answer. So these are the kinds of things that we typically are using RLVR in order to teach reasoning. What's not typically a domain used for RLVR would be chemistry, uh, um, uh, literature. You're looking for things where there's a very crisp, clear binary. Did you get the right answer or not? Because what we're not looking for is like word for word, we know what you should say. We're just looking for you to get the right answer. So if you ask for a function that, whatever calculates the factorial, there's probably more than one valid program. Um, so they don't all have to be character identical to, even if you have a canonical answer, as long as they do the right thing. All right. So these current methods for RLVR, predominantly we're talking about GRPO. Learn only from a scalar outcome reward per attempt, creating a severe credit assignment bottleneck. So there's a diagram that might explain it a little better, but I'll just say briefly, if your LLM spits out 200 tokens saying, well, first I think this, and then that, and then the, so my final answer is 35. Um, if it gets it right, then all 200 of those tokens in the answer get upvoted. And if it gets the answer wrong, all 200 tokens in the answer get downvoted. And so that's the credit assignment problem, is that you're not really finding where it went wrong in its thinking. So this seems to be a low information scenario where you're just getting a 1 or a 0. So they point out that many verifiable environments actually provide rich textual feedback. So you might get a runtime error or some other kind of code error message that explains why your attempt failed. And today, even if you run, if it's supposed to generate code, even if you have an environment where you run that code and you get these error messages, we throw those error messages away. We don't actually show them to the LLM. We just say, nope, your code didn't work.
Hmm.
So they're going to formalize a setting of reinforcement learning where they have this rich feedback. They have something other than just did you get it right or not. And they're going to call their algorithm self-distillation policy optimization, SDPO. And it's going to take that tokenized text-rich feedback and it's going to convert that into a learning signal that we can then run back propagation on. Many, many other papers have done something with this sort of extra information to say, oh, we know more. We know that when you first tried to solve this problem, you got a division by zero error, something like that. Okay. What this paper is doing very different is how do you actually take that information and turn it into a weight update? That's the thing that mostly people have not been able to do. Okay. Even before we did reinforcement learning, people just did sort of longer context, right? You can just tell the LM, try this problem, it gives an answer, and then you could say, hey, I got this error message, try again. It'll generate new code, right? So we've done, lots of things like that. But how can you actually bake it into the weights so that model does better on the first try in the future? What SDPO does is it treats the current model when it's conditioned on both the feedback and the original problem as a self-teacher, separate from when you originally asked the question, it didn't have the feedback, it just had the problem. So it's saying problem plus feedback is more information in the context than just problem alone. And it's going to take that, and we'll see the method for distilling the feedback informed next token predictions back into the policy. So the goal, the hope of this is that the model will identify its own mistakes in context. And in particular, it will pinpoint where those mistakes happen. So, for example, in our 5 times parentheses 3 plus 4, if if the LLM generates, I will start by multiplying 5 and 3. What we're going to see is that it's possible that when it has this teacher feedback, the teacher's going to say, I will start by, those are all fine tokens. And then it's going to say, wow, that next word you said was multiplying. I would have actually used adding as the next word there. And so we're getting individual token wise strong feedback instead of for GRPO, all the tokens get upvoted or all the tokens get downvoted. In this scenario, some tokens can get upvoted and others can get downvoted. So of course they have benchmarks and they say that, on this coding, LiveBench v6, SDPO improves sample efficiency. That's what I was talking about, where it learns faster and it achieves a higher final accuracy at the end of training. SDPO also outperforms baselines in standard RLVR environments that only return scalar feedback by using unsuccessful rollouts as implicit feedback. I'm sorry, by using successful rollouts as implicit feedback for failed attempts. So mostly we're going to talk about this rich feedback, error messages, things like that. But they did try another thing where they said, uh, if sometimes it gets the answer right, sometimes it gets the answer wrong, can we use that to form the teacher that gives us the feedback signal? And then they finally tried a third scenario where they tried it on really hard problems. And so at test time, other people have other test time techniques where you actually are training the model at test time on just this one problem. And so they're kind of running the problem over and over and over and over again. And this is not a great technique yet. We haven't really figured it out. But we have seen where models can get a little bit better. And they found that this worked better than GRPO in that particular setting as well. All right, so that's the high level. Any questions before we dive into the details? All right. So section one, repeats a lot of stuff in the abstract. So they say GRPO, which is our dominant recipe, is bottlenecked in terms of credit assignment. So if you have a 200 token answer, they all get a 1 or a 0, basically. You have a 2,000 token answer, they all get a 1 or a 0. You have a 20,000 token answer, they all just get a 1 or a 0. All right. Um, so that's really the key limitation that they're looking to get around. And so the key thing here is they say LLMs, decently large LLMs, already possess this very, very powerful method, this mechanism, which is in context learning. So in context learning is the reason why things like few shot actually work really well. So if you if you want the model to do a particular something or whatever, imagine that the LLM had never heard of Pig Latin before, and you said, "Oh well, we're gonna whatever the rules are for Pig Latin, we're gonna take the first letter, the first sound of the word, and we're gonna stick it at the end, and we'll add, ay whatever to the end. So, pig becomes ig peg, whatever. If you just give it a handful of examples of how to change the word, then the model says, "Oh, I've seen these examples, and it can now follow those instructions further on." In that same way, what they're hoping is by putting the error message or whatever that kind of information into the context, even though you're not telling it very specifically what line of code caused this error or anything like that. That's just enough of a hint that it'll do a slightly better job answering the second time. And we don't even need for the model to predict different tokens um, when it has this extra feedback information. All we need is for the likelihood of each token to change a little bit. So in my made up example where it said multiplying instead of adding, if the probability of the word multiplying was 55%, the probability of the word adding was 25%, we don't need to, in one pass, completely change the probabilities so that adding is now over 50%. All we need to do in one step is to just downweight multiply a little and upweight adding a little bit. And then if you run this algorithm, right, over a large training set, all of these little differences will keep adding up. And eventually you can get to the point where adding actually then surpasses multiplying. So you have to remember that models, right, we train them over many samples. This doesn't have to happen all in one fell swoop.
Can you maybe you get to it later, but can you give me just kind of concrete example of like what gets added into the context for the next cycle?
Yeah. I think that's the key thing to understand. There's not a super great diagram. I have some notes in the margin that I scribbled. So before we get to that, let's talk about table one super quick here. Okay. So there are already techniques in which you can make an LLM better. In particular, if you wanted a really small model, let's say you wanted a 1 billion model that you were going to stick on your phone, okay, you can use techniques from bigger, better models in order to make your model better. Okay. You can do the original distillation along the lines of the 2015 Jeff Hinton paper. Okay. Um, and you can just do fine tuning on the logits from this teacher, and you can improve your model. You can also do on policy regular RL, where instead of doing supervised fine tuning, you're doing RL, but your reward signal is coming from this strong teacher. Okay, everybody knows you can do this. The problem with this, though, is you need this strong teacher. You need some better model that's already trained. So if you're in a situation where you have that strong teacher, you should go ahead and use it. But when you're at the frontier, and in a lot of situations, you don't actually already have one. So that's really the scenario they're trying to address in this paper, right? So in the scenario where you don't have a strong teacher, you get to the bottom two rows. There's GRPO, which is on policy, which means you're giving feedback on the predictions from the actual model. But the signal's very weak, primarily, you know, a one or a zero on every sample. And then in their paper, they're going to check all three columns. They're going to say you don't have to have a strong teacher in advance. It's going to be on policy where the model learns the fastest, and we're going to use rich feedback. So how does this thing actually work? Um, for notation, we're going to say that our model is pi and its parameters are theta. Okay, so regular note next token prediction, okay, is of the form, you know, my policy pi of theta is going to predict the next token given the problem X. And the problem X could be, you know, something like this, you know, write a Python function that returns all numbers from 1 to n, something like that, okay? In this case, they say the feedback, then it writes some code, okay? And in our verifiable reward environment, they're able to run this. And I don't think this is necessarily realistic feedback, but the feedback is don't include n. So when they say 1 to n, they really only mean 1 to n minus 1. Okay, so 1 to n, not including n. So then what they do is the teacher gets a prompt that's something along the lines of write a Python function that returns all numbers from 1 to n, answer briefly. In a prior attempt, you got the feedback message, don't include n. So there's no code here for it to compare to. There's no nothing. There's just, huh. And so this is a kind of simplistic example, but as a human, you might imagine if somebody warned you that you tried to solve this problem and it included n and that was a bad thing, then you might be like, okay, let me figure out how to write a Python function that returns all the numbers, but don't include n. And then you might do a slightly better job answering this problem. Okay. And the key thing is not that you have to get it right. You just have to have slightly better next token predictions, which we're going to use in order to do a gradient update against the student model. So I still haven't showed how we actually get that signal. Okay. But for notation, so pi of theta, predict the next token given x. And then for the teacher, it's going to be pi of theta predict the next token given both x and the feedback. So that's example, like I said, where it's write the blah, 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 blah. Note that in a previous attempt, you got the following message. Don't include it. And then that's all it is. That it's just adding a few tokens to the prompt. So you can imagine the original prompt might have been 1,000 tokens. X comma F is now 1,100 tokens. There's a few extra tokens, a few extra words. All right. So the algorithm I found, I'll go through the algorithm, but I found that it helps to have a little bit of a picture here. Okay. So you're going to sample questions from the data set. Okay. Questions X. So, write a function that does blah, 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 blah. And then you're going to sample a response. You're going to let your model respond. You're going to then run it through and it's going to get some feedback. The feedback might be don't include n. The feedback might be I got a division by zero error on test case 3, whatever. Here's the self-distillation thing, okay? We're now going to take our LLM and instead of just giving it X, we're going to give it that X plus that extra feedback. Don't include n. I got a division by zero error, whatever, whatever. And then this is the part that I had to kind of think about for a second that was a little bit not clear to me on the first reading is it says also here, I'm predicting the next token based on output tokens less than t up to the current token. So what does this mean? This means that I'm using all of the student model, all of the original model's token predictions. I'm not actually generating a full answer. So we don't ask the teacher, solve this problem. There are plenty of papers that have done that. They say, teacher, solve this problem. Now, what do you do with the teacher's answer? How do you turn that into a back propagation signal? So I scribbled in the margin here a little diagram. Okay. So here's our student model, our original LLM, the one that we want to improve. And we have this long prompt that says whatever system prompt, blah blah blah, write a function that does whatever. And it says I think the first token. Um, so I let's say this is some word problem. It's like Mary has 4 apples, and then Mary doubles the number of apples. Then Mary gives away 2 apples. How many does Mary have left? Something like that, right? So you say, here's this whole problem. Um, how many apples does Mary have? And the model might say, oh, the first token I'm going to predict is Mary. And then when you're decoding, what do? You take that Mary and you copy it to the bottom, and then you run the model again on, all of this plus the token Mary. And then it says, oh, I think the second token should be hats. All right. And then you stick that on the end and you say, what is the next token? 4. Okay. The teacher sees not only the problem, but also this extra few tokens of the input that have the whatever message. And then it has its first token prediction. But we do not copy the first token down here. We always use the first token from the student. So we put Mary down here. And then it predicts the second token should be whatever. Whether it agrees or disagrees, we always take this token has and we stick it down there. All right. And conceptually, you do this one at a time. In practice, since you actually have all of the tokens from the student, you can actually plug them all in here at once. You don't have to actually do it one at a time. Okay. Then what are we doing? We're saying um, there was a set of logits, a set of token predictions that produced Mary. Okay. But there's a whole probability distribution, and we sampled Mary as the token that we were going to output. But we have the whole distribution. So if our vocabulary is 100,000, we have 100,000 probabilities that add up to 1. Here we have 100,000 probabilities that add up to 1. What we're really doing is we're saying we're going to compare this set of 100,000 probabilities to this set of 100,000 probabilities. And if you do a cross entropy thing, for those familiar with the math and the statistics, this is the KL divergence. Okay. So the KL divergence gives you a signal for how much this distribution, in this case, it's a discrete distribution. There are also continuous distributions. There's a discrete distribution over 100 possible outputs. And this is a discrete distribution over 100,000. And the KL divergence, we calculate between those two, and that's our loss function. And then we just back propagate against that loss function. So what's happening is we're just token wise by token, taking the first token prediction, the second token prediction, the third token prediction from the student to teacher. We see how they differ. And by back propagating, we're making the weights in the student more like the teacher. All right. But this is back propagation, so we're only taking a small step. So the key idea here is almost every other paper, instead of forcing the student's output as inputs into the teacher, they let the teacher actually generate a new output. And once you let the teacher generate that new output, people don't know what to do with that output. How do I actually shove that back in? And so the key difference between this and other papers that I've seen is this business right down here of forcing the student input into the model. So if you guys are familiar, when we pre-train LLMs, we scrape the internet, we get trillions of tokens, and what do? We do the exact same thing. We force all of the tokens in here. And during training, it doesn't matter what the model predicts the second token is, the third token is, the fourth token. We don't use any of those. We use those to calculate the loss and to back propagate, but the inputs are always completely forced from whatever our training sample is. So in pre-training, we call this teacher forcing. All right. In this case, we're still forcing, but what we're forcing is kind of backwards. We're sort of forcing the student tokens in here, not because these tokens are good, but because we want to see the teacher's reactions to these tokens. And so the teacher may say, your first token, okay, I'm okay with that. Second token, yeah, I agree with that. Ooh, third token, you said multiplying. I really would have gone with adding there. So when there's a really big difference in opinion, that creates a very strong backpropagation signal. When the teacher mostly agrees with the tokens that you output, then you mostly get sort of a zero signal in the backpropagation. And so the idea here is that SDPO, if we scroll down to, it's a different problem. Um, so this is the one with the output the numbers 1 through n. In GRPO, if it gets the answer wrong, if it says range 1 comma n plus 1, then it says, oh, you got it wrong, and every single token you see here is red, gets a negative signal. In SDPO, the model outputs range parentheses 1 comma n plus 1 close paren. And the teacher model, which is again, it's just the student model with that extra feedback in its prompt string. It says, okay, you can see light pink here. I slightly disagreed uh, with your choice here. I would have just gone with range instead of paren range, but whatever. Um, the model was thinking maybe I would have said, parentheses n here, or I might have said these other things. Um, and then you go along, but the teacher very, very strongly says, whoa, wait a second. Um, you did range parentheses 1 comma n. I thought you were going to do close paren here. So the blue is the one the teacher upvoted, and the dark red is the one the teacher heavily downvoted. So there's going to be a really strong signal, a learning signal on this plus token. And that's what's very different from GRPO, where you're getting this peanut butter signal across all of them. STPO can learn more efficiently if the teacher does a really good job of pinpointing exactly the tokens that it disagrees with. So you'll notice that even though the teacher wanted to say range paren 1 comma n close paren, that's not what the student said. So it has to then predict what should be the token that comes after plus. Even though it didn't want plus to be the next token, it has no choice. It's only commenting on all the tokens that the student output. So one of the things that I thought was interesting is the teacher's like, oh, well, I didn't really want you to do plus, but if I say zero here, then that's the same thing as just saying n, because n plus zero is the same thing as n. So zero was one of the most heavily upvoted tokens by the teacher. Um, and so here you can see again, you're getting very specific individual token feedback instead of this broad range. All right, so I'm going to pause here because this is really most of the algorithm. We could talk a little bit about the results and whatever, but the key thing is, again, almost all the other papers do a new rollout with the extra information, and then they try to do something with it, put it in the context, do this, do that, do it. Here, they avoid doing an actual teacher rollout, but they just have the teacher comment on, given the first however many tokens that the student output, would I have output the same next T plus one token? And they found that that was enough signal that the model did, in fact, get a learning signal. My guess is I'm virtually positive the teacher is not going to 100% of the time have a good learning signal. But you're doing thousands of mini batches and whatnot. And so you don't need it to come up with a perfect learning signal every single time. You just need it on average to be giving a good signal. And so what we're seeing here is that on average, it does do a good signal, and the signal is very individual word, individual token specific, whereas GRPO is not giving very, it's just simply saying your whole answer right or your whole answer wrong. So, you can imagine that like, I don't know, like somebody in middle school and they're in English class and they have to write a grammatically correct sentence. And anytime they make a grammar mistake, the teacher just says, this sentence is wrong. They don't tell you why it's wrong. They don't tell you whether it was a spelling mistake or it was plural or if it was past tense, capitalization. Nope. They just say this sentence was wrong. You might struggle wandering around for a while trying to figure out how to improve your sentence. Whereas the hope is SDPO is going to say, no, 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 no. This is exactly where you went wrong. All right, let me pause and see if there's any questions.
Um, what are those four rows? It says on the left it says vocabulary. Oh, but
Yes,
uh,
yes.
yeah.
So what's happening is um, if our vocabulary is 100,000, then the student generated parenthesis range. But we're actually going to record all 100,000 probabilities for every possible token it could have output. So there's parentheses range, dog, pencil, good, bad, green, blue, all 100,000 tokens. Um, we are looking at the probabilities. And then for the teacher, where they show red or pink, it means that the teacher's probability for that token was lower. And where it's blue, it's the teacher's probability for that token was higher. Okay. So what you don't see on here is apple, blue, pencil, because all of those are just much farther down the list, all super, super, super low, unlikely vocabulary words for the next token.
Mm. Oh, yeah, I
So,
see. Yeah, yeah.
so in fact, like here at this token position, where it says I really, really wouldn't have said plus, I would have said close paren. Okay. It's actually not saying just that. It's saying there's 100,000 possible tokens, and you had this high probability for plus, and I would have had a very low probability for plus. And you had a low probability for close paren, and I would have had a much higher probability for close paren. And it's actually saying that for all 99,998 other tokens as well. It's comparing the probabilities for every single possible next token.
Mm. Yeah, yeah, I think I understand. Thank you.
Yeah. Any other questions?
I have a couple. Um,
Okay.
First one, just looking at this, I get the loss function. I'm trying to understand what happens after we've found the big divergence, um,
Yeah.
where the plus should be converted to paren.
Right.
Do we
So it's
continue
not
to feed
converting
it?
anything. It's just simply
No,
saying the
it's by it.
probability
Yeah,
of this should be lower and
yeah,
the probability of this should be higher. And then when you backpropagate, you're just simply saying what change to the weights would have pushed this probability down. What change to the weights would have pushed this probability up.
yeah. I, I'm wondering though, so after I'm going to provide this loss function for every token position, right?
Hmm.
Um, well, okay, maybe it does make sense. If you had made the choice of that first row up through the plus, then what would my choice for the next token? Well, we're going down the wrong path, but zero would work here.
Hmm. So then
Okay,
that will
maybe
also
that answers
provide a little bit of
a little bit
training
better.
signal
Yeah,
going back into the weights. But for example, for this comma, it might be the case that every possible vocabulary word, all 100,000, the teacher has virtually identical probabilities to the
right,
student.
right.
And so it's not really saying if this was good or bad. It's just saying I don't have any change that I'm suggesting.
Yeah. I guess in this example, I can understand the zero and how the loss function would there work there. If the teacher believed that this was an irrecoverable mistake, what value does it add at the next token location? It already thinks you've messed up. So
So, um, so for example, this very last token, okay, so the teacher is forced to say, if so far we have said range paren 1 comma n plus 1, what are you going to say next?
yeah,
Okay. The teacher might be like, oh shoot, this is just wrong. I don't know what to do. And it looks like it kind of agreed with closed paren, you
Right.
know? But it is entirely possible that once you've hit a really bad mistake, the teacher's learning signal might not be very good anymore
Yeah, that's kind
because,
of where I was going. Yeah. Yeah.
you know, so if I said to you, Sally has 4 apples and then she doubles the number of apples and then she gives away 2 apples, how many apples does Sally have left? Right? And if your first 3 tokens are, Captain Ahab smiled, like I don't even know what to do
Right.
next to try to answer the problem. How many apples does Mary have? Right?
Yeah.
So it is possible that the teacher could, after a mistake, get very frustrated and not really know what to do.
Yeah, that's why I was almost wondering if you had something that would detect kind of the first significant correction and say, well,
Hmm.
the rest of the stream doesn't really help. But
Oh, that's interesting. Yeah, yeah. Yeah, maybe you could do a variant where once you have a major correction, you down weight the learning
the
signal
balance,
after that.
yeah,
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 I like that.
yeah.
That's very cool.
Okay, so
Yeah,
that was
and if they're
question one.
all small, then you just use them all. But if you
Yeah,
see a really big one, then at some point maybe you say I should. It's a trade-off because then you don't have as much feedback, but maybe you have only really good feedback.
yeah. And maybe there are times when there's an independent correction that you could do later on. If
Hmm.
it did this generate, 1 to n 3 times, maybe it could correct each of the three in the same way or something. But
Hmm.
okay, so that was the first one. The next one, can you roll back? Because the part that I don't get, it kind of feels like magic here. I guess it was a little further, is where this feedback signal. Oh, yeah, we'll go down. Yeah. Where was the feedback coming from? Where did the F come from?
Good.
Yeah, there you go.
So we are we are assuming this is reinforcement learning with verifiable rewards. So we're assuming that this is an environment that actually has some kind of error messages or other kind of extra information. Okay. If you were just doing a multiple choice exam and the only thing you know is you got it wrong, then you couldn't run SDPO the way we're talking about
Okay.
it. Okay. It has to be something where it's like you literally took the code that the LLM wrote and you plugged it into a REPL and you ran it on some test cases and you got some type of error message, and then
Okay.
that's what you pasted in
Okay. So I was thinking more like syntax errors or something like that,
here. Mhm.
um, rather than this verifiable, which a syntax error is a part of
The
that, I
syntax
suppose.
error is verifiable that your code is incorrect.
Right. And so would it if if I encountered a syntax error here instead of a logic error, um,
Yeah, then they would paste that here.
something would you're expecting the verifier to somehow provide this richer feedback of no, not only did you get it wrong, but you didn't compile, you had a syntax error.
Mhm.
Okay.
Yeah.
Um,
And so
and
so the degree to which SDPO can take advantage of this depends on how frequently, how much, how good
yeah,
this feedback is.
yeah,
If the feedback is very poor, like in my early days of programming, right, you just get like uh whenever we had like pointer errors, you would just get like invalid memory error, whatever. Like that's not really telling me anything.
yeah, yeah. And then the the other part is I'm kind of surprised there is no position, no token position information provided in the feedback, or maybe it's just not required. I mean, perhaps you could optionally include it or something.
Yeah, so let me go through some of the results really quickly. What they found was instead of just saying, here's the feedback, what
Uh-huh.
they could do is they could paste the code that the student wrote in the previous run
Okay.
and the feedback And what they found is that the algorithm didn't work better. Now, they did this on models only up to 8 billion.
Okay.
Um, and what they found was by pasting a copy of the student's answer, the teacher tended to be biased towards repeating the student's answer.
Yeah.
I think there is, in our pre-training, there is something that biases the model to be more likely to repeat things that it's already seen.
I think
And
attention
so, in
in
fact,
general
there's a
does that.
table where they show that if you had let the teacher generate its own answer, 13% of the time, it would generate the same answer without the feedback. Okay. When you include a copy of what the student did, even though you know it was wrong, 30% of the time, it would just produce the same answer that the student produced.
Hmm.
So they found through experimentation, through trial and error, that telling the teacher what kind of situation could arise, but not where it arose, actually worked better. I wonder if you did this on larger frontier scale models, if the teachers would then be smart enough not to just copy the student, and if it would actually work better the way you're saying, where you not only give it the error, but you tell it where the error happened. In some cases, right, the if it's code, you'll get the exact line number or the exact
Yeah,
tokenization
exactly.
where the error
Exactly. And
happened.
it seems
Yes.
like by not using that, we're throwing away valuable information.
Yes. So they
So, but
so
the
they did
reason,
consider that and it worked worse. But I do wonder if you use bigger models, I think that might change.
yeah.
Right. And you could also just include something in your system prompt that says, don't copy what the student did, you
Yeah.
know.
In general, does language models have a kind of a bias, a tendency to just repeat patterns they've seen before?
Yeah,
So I
I
wonder
would
if there's a way to counter that.
Also,
in
like I'm not sure where I think generally speaking, don't you do reasoning fine tuning after preference fine tuning?
I don't know that one, but I will contribute on the I think I might call it the most common failure mode of especially text-based language models. To once there is enough structure in the context window, they will unless there is something especially interesting attention-wise, they will just default back to pattern matching, in my experience.
Mhm. Yeah.
Yeah.
Um, it's a completely different phenomenon, but like earlier versions of Nano Banana, um, sometimes I would ask it to make a change and I would just basically get back the exact same image. It's very frustrating. It's like I would feel less angry if you tried to change and made the wrong change, but you just gave me back the same image.
If you think
All right.
about it, the way that the attention mechanism works, since it just sums up the cross product across or the dot product over all locations, all sequence locations. If you have a match, imagine like separate out the position encoding, just if you're running nope on it, and you have a word that shows up, a token that shows up, but it shows up 30 times. Well, its signal strength now is going to be 30 times.
Yeah,
That's the way I've always intuited that the repeat problem occurs. Um,
Yep.
Position
interesting.
encoding can cancel it out, but depends
Yeah.
how sensitive.
Well, I would be interested to see an implementation of positional encoding that actively tries to cancel it out. You know what I mean? I feel like
Well,
that would be a very,
I mean, if I understand the way kind of the query position dot product works, you can have a query that's very position specific, and then you can also have ones that kind of ignore more of the position. So yeah, so some queries might be more affected by repeat patterns than others. Nope being an example, an extreme, there's, essentially you're ignoring all the position encoding. And so all 30 times that something occurs all points you in the same direction and dominates.
All right. So looking at the time, let me just fly through a few um, things here. So uh, specifically here, they show some equations. So in GRPO, you are basically saying I have a batch, and I'm going to compare my rewards to the average of the batch. So in a batch, what you hope is you get some right, you get some wrong, and then the wrong ones get downvoted, the right ones get upvoted. Here, what you're doing is on a token by token basis, you're saying what's the ratio of the teacher's um, probability for that token versus my student probability token. And so in doing this, they're saying GRPO, you get 1 bit of feedback for the entire sequence. Um, and so now we are allowing arbitrary sequences of token as feedback with the caveat that we still need a good system that gives us rich text back. If it doesn't give, if this allows these texts, then it's not going to be helpful. And then this feedback is done at the logit level. So basically, in GRPO, you get a 1 or a 0 for all 200 tokens in the student answer. Okay. In SDPO, you get 100,000 probability differences per token position. So 200 times 100,000, you get 20 million feedback signals. Now, the reality is most of those 20 million are going to be close to 0. Okay. But you can see it's orders and orders of magnitude more signal coming back to get 20 million pieces of feedback instead of 1. All right. That's the theoretical algorithm. Now they go to implement it and they ran into a few things. Okay. um, the first one is if you're computing this KL divergence on a longer answer, a 20,000 token answer, then you have to keep in memory 100,000 probabilities for 20,000 tokens, which is what's the math on that? 2 billion probabilities that you have to hold in memory just for this. Okay. So since most of the probabilities don't differ and are close to 0, what they do is they only use the top 100. Okay. So you're still getting a much richer. So if you have a 200 token answer, you're getting 20,000 feedback signals instead of 1. The other thing is, not going to go into this, but in RL, you can wind up with these sort of instabilities, and you can have weird feedback signals and whatnot. And so one thing you see fairly often in RL literature is some version of I'm not going to do an update based on the instantaneous thing. And they do the same thing here. So for the teacher, one of the things they do is they do an exponential moving average. They say, I'm not going to use my student. I'm going to use this exponential moving average, and that avoids some of these race condition instabilities. The downside is this is where the extra memory comes. The original raw theoretical algorithm, you're just adding that extra F to the prompt, that extra feedback to the prompt, and you only need 1 copy of the student model. As soon as you say, I'm going to use a different thing for the teacher, I'm going to use the EMA version, now you actually need to have 2 copies. You need to have the student model and the teacher model. And so if you're training GPT-5, you can imagine 2 copies. That's a pretty significant thing. I suspect if people like SDPO badly enough, people will find other ways that don't require having 2 full copies of the model. Maybe if you just have an EMA on the last 4 layers, that's enough to remove the instabilities, you know. And so you don't have to have 2 full copies of the model. You can have 1 copy except for maybe the last 4 layers or some other kind of trick, you know. All right. So in the experiments, uh, um, section 4 is what we've been talking about, where you're doing coding or something else that has rich feedback. They did the experiments. And essentially what they found was that SDPO learns faster, and models from 500,000,000 to 8 billion, they found that the improvement over GRPO was bigger the bigger the model. And again, this is because the teacher is using in-context learning. It's getting this weird error message, but not being told exactly where the error message happened. So it needs to be pretty smart in order to be able to leverage that information. So there's the possibility that as you get to bigger models, as you get to a 27, you get to a 70, you get to a 500 billion model, this gap could actually get even bigger. It's unlikely to get smaller, but so that's a good size, a good sign. Um, they also did an ablation where they said instead of doing the full SDPO algorithm, where like we say we take the top 100 predictions for every token position, what if we only took the top one? Now we've reduced it for a 200 token answer. We've reduced it from 20,000 feedback signals to just 200 feedback signals. What if we went even further and we said, we're going to take the teacher and we're going to average all of the top one token probabilities. So now we only have one feedback signal, same as GRPO. We just have one number. And then here's the chart on the left. And unsurprisingly, the full algorithm in green does the best. But what I found surprising is that in blue, this is the SDPO where you averaged all of the contributions from all 200 tokens into just one number and applied it to all tokens equally. So it's essentially very similar to GRPO. They're all getting a peanut butter feedback. The main difference is that the way SDPO calculates the strength of that feedback is based on its token by token probabilities, whereas GRPO, it's just all or nothing. You got the problem right, you got the problem. I'm not really sure why this gap is so big between the blue and the gray, but my intuition is that um, if you got the problem wrong by making a one-word mistake in a coding problem, then you did get it wrong, but SDPO is probably going to have a fairly small negative signal because most of the tokens it agreed with. Okay. Whereas if your approach was completely bonkers and it just utterly disagreed with everything you were doing, then you'd get a very large signal. So it seems that maybe SDPO is able to have a little bit more nuance in between, like, you got it. I don't want to quite call it partial credit, but you got it a little bit wrong, or you were way off. You were just totally barking up the wrong tree. Um,
I like the
this,
partial credit analogy. That seems pretty
yeah,
close.
this gap between the blue and the gray is one of the reasons why I am most excited about SDPO. Because even when they got rid of this extra positional token by token feedback, it still beat GRPO. That says to me that this fundamental idea of feedback, this partial credit, if that's what it is a good learning signal. And you don't need super awesome feedback that pinpoints the exact token where you made a mistake, right? If you do have all of that, then you move up even higher to the green. But so this says to me that we could do variations on STPO, we could do different things, we could do something to try and reduce the memory cost, blah, 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 blah. And that all in all, we're still, doing something that's a lot smarter than GRPO. All right, I think that's, yeah.
I was going to ask a question, Ted. I think I remember, but could you real briefly cover GRPO?
Uh, the fundamental for GRPO is you have to do batches with GRPO. You cannot just have a single response.
Yeah.
Okay. And so you do batches. So let's say it's a coding problem. You have a batch size of 8. You get 8 different answers. You figure out what the average reward is. So if it got 2 right and 6 wrong, the average reward is 0.25. It got a core of them.
Hmm.
The advantage is just defined as my reward minus the average reward. So for the two entries that got it right, they're going to have a 0.75 advantage. And for the six that got it wrong, they're going to have a negative 0.25 advantage. And that's where, in this example, we saw where to go. Oh, I'm past it. Um, there. Whatever that advantage is, every single token gets the same plus or the same minus.
Right. So that's what I was wondering if this makes sense at all, that there's kind of two differences. One, the way you're determining the better response is different between GRPO and SDPO. And then the second is how you're assigning that credit. I wonder if you could do a GRPO type um, determination of which is a better answer, but you apply more of a SDPO style assignment. I have a loss function like the SDPO. So, if I have GRPO, I've got one that's good and one that's bad, but they started the same. I don't need to adjust the parts that are probable under both of those. I just need to adjust the weights that affected the wrong choice. Does that make sense what I'm saying?
Funny you should ask about that because the next use case, they did something exactly like that.
Oh,
Um,
sorry.
so so in this case, they said, what if you don't have rich text feedbacks like error messages? Okay. So they tried some benchmarks for chemistry, physics, biology, da 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 da, and they did the GRPO thing where they did a batch of of responses,
Hmm.
hoping that some would be right and some would be wrong. Okay. And when that happened, then instead of the feedback string F, you know, I got a division by
Right,
zero error, syntax error, whatever, they pasted the correct answer from one of the other entries in the batch.
right.
So basically, the prompt is now answer this blah, 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 blah question. Somebody else got it right using this answer. Now, normally you and I would think that's a terrible prompt because now you can just copy the answer.
Hmm.
But remember, the teacher's not allowed to output anything. It's getting forced its inputs. So it might try to copy the answer, yes, but it's going to do it in a way relative to what the student's answer was.
Right,
And so, like in the coding problem, you can see it's like, yes, range, yeah, I agree with that one. Yeah, paren, I agree with that one, and I agree with that, comma, I agree with that. Whoa, buddy, what is this plus sign over here? I do
right.
not agree with this, right? So it could do it in that form, or it could do it in a way that's a little bit more nuanced. But the bottom line is it's given one correct answer and it token by token just upvotes, downvotes the student's original answer. And they found that this did work.
It did. Okay.
Yes. Of course they found it worked. Well, it's paper. No, but this is the section where they said not only that, but they found that the correct answer. So if you see these benchmarks, you're like SDPO beat GRPO. But the other thing that happened was the average length of the answers on correct answers was shorter. That they both used chain of thought reasoning to get to their answer. But SDPO was able to get to a correct answer more often, even with shorter answers. This is a very cool result. If this result persists, this does two things to you for you. One is maybe SDPO is actually doing a smarter kind of reasoning. And two, even if it's not a new paradigm and it's just doing the same kind of reasoning, it just happens to be doing it a little bit more efficiently. Can you imagine if you have this 5 hour, Claude code task? If everything that these agents are doing generates 50% fewer tokens, that means that on your same token limit, you can do double the amount of computation
Mhm.
and still have the same inference cost. That would be really, 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 really awesome. So to get any kind of improvement there, right? 20%. It doesn't even have to be, said on these chemistry ones, it was like, I don't remember how much shorter. It was like a third the length. So it was like this massive, massive reduction in answer length. But even if you just got, you know, a 20%, a 7% reduction in length, think of what that means for OpenAI, for Anthropic, if they could get all the same answers, but just reduce token count by 7%. That's probably millions, zillions of dollars a day. So these are some of the things about SDPO that like, oh yeah, maybe we need to tweak the algorithm a little and improve it. I love your idea about maybe you weight things after the first major change. Maybe we tweak the memory footprint, but there's so many good things coming out of this. So it's exactly where you went, Roger. They said, yeah, maybe we can actually apply this in a more GRPO-like thing. If you have rich rewards, let's use them. If we don't, we can kind of do a more GRPO kind of thing. And then finally, the last use case I don't talk about too much. I haven't quite wrapped my head around. That's the test time one where they said, oh, here's this coding problem and it's super duper 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 hard. And you can't do that trick we just talked about because if you do a batch of 8 tries, all 8 of them are going to get it wrong. So there's no delta signal there. Okay. But if you do have error messages, they said we can plug the error messages in and we can do the teacher feedback thing like we originally talked about. And then the next time around, it's still going to get 8 of them all wrong. But we're going to get a little bit more teacher feedback. And we're just going to repeat on only this one problem. So this is no longer training time. This is test time. I'm just going to do this one problem over and over and over and over again a bunch of times. And I'm going to update the weights on my model. And people have done this with GRPO, and a certain percentage of the time, it'll actually get problems right that it was originally getting wrong. So a similar, slightly more higher percentage of the time SDPO worked, but when it did work, it got the correct answer in fewer repetitions than GRPO took in order to get there. So once again, we're seeing it's more sample efficient in order to get there. In this case, I don't think it got to, I don't know if they have numbers. I don't think it got to a completely better, a much higher number of them. But it solved a little bit more and it did it more sample efficiently. So that's the final use case. And so, yeah, so all in all, this reasoning stuff I think is very important. Um, Best case scenario, SDPO is actually teaching a different kind of reasoning. Uh, um, but what would be satisfactory is even if it's not teaching it, if it's just teaching it faster, teaching it slightly better, teaching the model to gets to the right answer without as many, wait, let me redo that. All this backtracking, circling and stuff. You need a certain amount of considering different options, but sometimes you can get, you know, huge backtracking thing, right? Like those early papers where they did that, you saw if you asked it a really simple question, like, Sally has 5 apples, she doubles the number of apples, she gives away 3. How many does she have left? And like whatever it was, you know, um, DeepSeek R1 or whatever, could burn 5,000 tokens just saying, well, Sally had 5 apples and she doubled it, so she would have 10 apples then. But wait, maybe that's not what the word double means. And then it tries something else. It says, but wait, I did 5 times 2. Maybe I should be doing 2 times 5. And so you see, it'll just burn thousands of tokens, circling, 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 you know. And so maybe that's the only thing that we avoid is some of that unnecessary circling. But there's just multiple ways in which this algorithm could win. If all of them are wins, then this is huge. But even if any one of them is better GRPO, then I think it still makes room for this. So hopefully we'll see some better reasoning.
Is that the instinct as to why that answers are shorter? Is that it rather than just rewarding or penalizing based on the final answer, it's looking for errors along the way?
I
And
don't really have an intuition as to why it got that. They just say, where is it? Um, things like no, wait, um, um, you know, sometimes GRPO says, wait, I'm going in circles. Uh, so they said, yeah. So in this, I guess they might be cherry picking, but they said in this one chemistry problem, GRPO said, five times, no, nine times, wait, 25 times. And so STPO just didn't have as many of these kind of, circling back.
Wow, and
So
it's 7 times shorter?
that
That's
was just this chemistry one. It didn't do as well on all the other
okay, because that's pretty
ones.
significant.
Yeah. So chemistry was the one that it actually had the biggest improvement in scores. So like 76 versus 54. And it also had the biggest improvement in terms of shortening. So maybe there was something good here. But overall, it gave shorter answers and it gave better. It did better on the benchmarks. So
Hmm,
pretty nice.
cool.
Um,
Was
um, sorry, Ted, you said that you have three plus and one minus for
Mhm.
this. Well, what
Yes.
is that one minus?
More memory.
Oh,
So when they didn't use the theoretical algorithm, but the practical one with the EMA, that means that you need to have a second copy of the student that you are moving averaging.
ah,
Um, and so you have the current student and you have the EMA student that you use. Um, and I'm not sure if I think there should be some clever way you can do EMA or partial EMA so that it's not quite as expensive.
hmm,
But the naive implementation of EMA would be you have a completely second copy of your entire model that has EMA weights instead of current weights.
hmm. So, so that means naively you need to double the
Yes.
memory. Okay, okay.
So
Thank you.
PPO has double the memory of GRPO. And that was one of the things that DeepSeek liked best about switching from PPO to GRPO was cutting their memory needs. Uh, PPO is doing a value function, so the value function needs to be very accurate. Here, the reason why we're doing the EMA is very small. We're just trying to avoid high whatever
Hmm,
fluctuations, spikes in the gradients. So I think there probably are a whole bunch of ways you can smooth that.
hmm,
Maybe you can just use clipping. Maybe you can EMA only a few of the weights. Maybe there's some other way you can smooth. You know what I'm saying? So I think that memory thing could probably be solved if the rest of this works well.
oh,
If you say, wow, it didn't just work on 8 billion, it worked on my 500 billion, my trillion parameter model really, really well. I wish it didn't take up so much memory. I bet somebody will come up with a different tweak that uses the core of what we talked about, the distillation, but just fixes the EMA memory.
hmm, okay, okay. Thank you.
Yeah.
okay. Should we stop the
And
recording then? Were there any more
Yes,
questions?
please.
uh, I have one more question. I think the paper said that the what is that? The advantage of this method is more obvious in a larger and more and a better model.
Yes.
Um, yeah, um, what's the what's the intuition behind that? Because yeah, when I'm thinking, oh yeah, maybe because it's like scroll the responses better. But when I'm thinking about it, when you have a really frontier model and and the response, the output will be already good. So then when you do the what is that? Verif verification, then a lot of time, then you wouldn't get a negative feedback. So would it still be true that when you have better model, you would get better, uh, more advantage from this method?
Yeah. So what the authors say is that the only way that the teacher is better than the student is if it knows what to do with the feedback message. Okay. And it has to use in-context learning. So because this is an academic paper, this was not like OpenAI research. They didn't have access to testing this on a giant model. So they only tested it up to an 8 billion Quen model. 8 billion's good, but it's not great, you know? And so 600 million is a very, very small LM. So I can
Mhm.
see why that tiny model might not have really been so smart about figuring out what does this error message tell me about what I should do, what I should avoid when I'm generating my answer. Um, so that's the intuition is that. And so it's possible that it just plateaus because above a certain size, all models are capable of understanding what the error message means. It's possible that maybe the gap gets even a little bit bigger because the models um, are better able to use it. And that's where Roger and I think we're talking about possibly an even bigger model. You can show it the original answer. And you can, if the compiler gave you pointed to where the error happened, you could show it the original answer and point to where it happened. They found it didn't work well for these small LLMs because the LLMs tended to copy, but a bigger model might be smarter about knowing what to do with that feedback and not copying it.
Hmm. Hmm. Okay.
You,
Okay.
Ted, one way you might be able to avoid that tendency to just copy is have the model review like the prompt, the generated code, and the error message. Don't generate new code, but generate advice and then put the advice back in. So the feedback essentially was kind of processed with the full context of the sample and the feedback.
So you mean almost like a two-step process? Like
Yeah,
you get the exact error message, you generate advice, and then you do X plus advice and have it do distillation.
right. Yeah, yeah.
So then it doesn't no longer
Can't
with the
copy.
advice, it no longer has the copy. It can't just copy.
Exactly, exactly.
Okay. Yeah.
Then maybe you could avoid the uh, exponential moving EMA copy if you did it that way.
Maybe. I think you still can get those weird feedback signals when you're
Mm,
doing updates on the exact same weights that you're generating from.
could be. Yeah, no, you're
There's a
right.
lot of like contrastive learning and reinforcement learning papers where
Yeah,
they have to have something to smooth
yeah,
those deltas. Otherwise, and maybe clipping is sufficient, but I think otherwise it's possible that maybe in some situations you have this phenomenon where you divide by 0.001 and you get this massive
yeah,
gradient.
yeah. Yeah, you might be able to provide a richer
Flipping.
signal, richer feedback signal, but yeah, you're right. It doesn't solve the EMA
Yeah.
problem.
I
In the
put
chat,
forth to the
somebody mentioned
council.
muon clip,
Yep, there you go.
and I think that's exactly um, potentially the same phenomenon. Is that is that you don't have this EMA or whatever when you're training the LLM with muon, and so um, you're doing this right. You're doing this orthogonalization of the matrix. But if something was potentially like close to orthogonal, but there was a 1.001 somewhere. I don't know exactly use it, there could be something where you then wind up with this weird thing when you're trying to orthogonalize it, where you end up with like some giant number or something like that. One or the other, either a tiny number or a giant number, and then there's the forward direction and the back prop direction. So you're either in the forward, if you're not dividing in the forward, you might be dividing in the backward direction. So either way, that could be really dangerous and just generate a weird thing, which clipping would avoid actually, taking a step based on that very bad rate.
Okay, 20 after. I'll
Yeah,
go ahead and
we
stop
should.
the recording.
Thanks.
Thanks, Ted.